Hello again! Now that we have established a coordinate system and have reviewed the shear force and bending moment diagrams, if that was necessary of course, we are ready to look at bending of beams. And we will start by looking at how a beam deforms and based on this derive the equations. But we have to start with an important assumption. We will be working with symmetric beams only in this course. This assumption is necessary to have a pure bending deformation. So let's start by defining what we mean by a symmetric beam. To do so, have a look at this generalized symmetric beam with the general cross-section shown on the right. As you can see, this cross-section is symmetric around the y-axis, and that brings us to the assumptions we have to make. The first assumption is that the beam section is symmetric about the deflection axis. Since we have a moment in x direction in this case, the deflection axis is the y-axis, since the beam will deform along this axis. The cross-section can be anything as long as it's symmetric around the y-axis. Another assumption we have to make is that the material used has the same tensile and compressive stiffness. Hence, the Young's modulus is the same in tension and compression. This final assumption may sound a bit strange, but the reason for it will become clear in a few minutes. For now, remember that these are the two assumptions that we need to derive the stress and strain distribution in a symmetric beam. The first step in deriving the stress and strain distribution is figuring out how exactly this beam will deform. And we will do so by looking at a relatively simple symmetric beam, namely a beam with a square cross-section, which is thus symmetric around both the x and y axis. For your reference, the coordinate system is also shown on this figure, so you realize what axis corresponds to which direction. On this beam I have also drawn a series of lines, so we will be able to see how the beam deforms when we apply a moment mx. You also see I have drawn a red line on top and a blue on the bottom. These we will use next to see how the top and bottom deform. And as you can see, we are applying a moment around the x-axis. Before going further, please take a moment and think about how this beam will deform. If we now look at how this beam deforms, we see that the bending results in a curvature. Now let's have a detailed look at this deformed beam. First of all, let's look at the straight lines that we had drawn on there before. As you can see, the lines that were in vertical direction connecting the top and bottom remain straight. They do rotate, but they remain straight. Hence, the cross-section will remain plane. Next, let's look at the red line that was on top. It seems to be compressed. It is on the concave curvature side and is shortened in order to be able to form that curvature. On the bottom side, where we have drawn the blue line, the opposite happens. This is the convex side of the curvature, and here the line is elongated, and thus there has to be some tension on this blue line. So we see that we have tension on one side and compression on the other side. Hence we know that somewhere in between there must be a location where we have no elongation and no stress or strains due to bending. This line is called the neutral line. In this specific case, due to the rectangular cross-section, I know that this line is in the middle of the beam, but its location may be different for other cross-sections. However, any symmetric beam under bending will have a neutral line in its cross-section where there is no elongation and no normal stress. So now that we have observed the deformation, we are going to use these observations and try to interpret it in such a way that we can find a formula for the stress and strain. So here we have our beam, and let's just replace the lines with a sketch of the problem. The red line on top, which is in compression, the blue line on the bottom, which is in tension, and the two lines on the side bounding the original rectangular part. And the line in the middle, which we just found out is the neutral axis. Now I just want to point out again that in this specific case the neutral axis is in the middle of the cross-section, but that will not always be the case. This neutral axis will always be the axis where no deformation occurs. Now this dashed line clearly has a certain curvature, and hence can be seen as a circle with a certain radius r. Do note the kink in this line, because the midpoint of the circle is laying well outside this slide, but this dashed line is thus a part of a circle with radius r. Now we want to figure out the length of the dashed line in between the black lines, now highlighted in orange and called ds. Based on the fact that this is part of a circle, we can calculate the arc length ds using ds is equal to r times d theta, where d theta is the angle that this part of the circle is made of. This is one of the parts we need, but there's one more thing we have to use. This line is along the neutral axis where there's no elongation. Hence, the original length of this part, dz, is equal to the deformed length ds. Hence, dz is equal to r times d theta. And this we can rewrite to 1 over r is equal to d theta over dz. This is the first equation that we will use later on, so remember this one or write it down. Now that we know ds in the neutral line is connected to the original length, we have to determine the length at a certain distance away from the neutral line, either above or below. We will do so using the same sketch as before, where we have now drawn another section AB, which is a distance y away from the neutral line. And here I want to emphasize again that this is a distance y from the neutral axis in general, not from the middle of the cross-section. Furthermore, the direction is important as well. AB is below the neutral line, and thus the distance y, used in this case, would be positive, since we defined the y-axis as positive downward. Now that we have a general part AB, we want to know the length of it, because once we know the length, we can use it to determine the strain, and from the strain we can determine the stress. But first things first, let's calculate the length. This length is given by the radius of the circle, RAB, times d theta, the angle that this part of the circle is made of. So the radius of part AB is clear from the sketch. It is the radius of the neutral line with the length y added. Next, we have to reuse one of the formulas of the previous slide. There we found that the original length dz is equal to r times d theta, hence d theta is equal to 1 over r times dz. Filling this in, we get r plus y times 1 over r times dz, which we can rewrite to dz plus y over r times dz. Since we want to know the strain, we have to recall that the strain is a change in length divided by the original length. This we can rewrite since the change in length is the length of AB minus dz, and the original length is dz. So filling in the expression for the length of AB, we find that the strain is given by y, the distance from the neutral line, which includes the sign, divided by r, the radius with which the neutral line is arched. Hence, the strain is linearly proportional to the distance from the neutral axis. Here we also see that we get a positive strain and there's an elongation when y is positive, which we also found for the blue line on the bottom. And above the neutral axis, y will be negative. Thus we will get a negative strain indicating compression, which we expected for the red line on the top. Now let's repeat the equation we have just found, since I want to look at it in a bit more detail. If we now look at an arbitrary symmetric cross-section as shown here, loaded with a moment mx, we know the strain will vary linearly, as we just derived. Hence, this is the strain distribution. Do note that the neutral axis, which is at the height of the x-axis, is now no longer in the middle of the cross-section. However, the equation is still valid for any symmetric cross-section, so we can still use it. This does mean that the maximum compressive strain on the top is larger than the maximum tensile strain on the bottom. But now of course we want to determine the stress, not just the strain. And to go from strain to stress, we need to use Hooke's law, which in general form reads epsilon z is equal to 1 over E times sigma z minus mu times sigma x plus sigma y plus alpha delta t. Luckily, in this case, we can simplify this equation considerably. First of all, we only apply a bending moment, no change in temperature. Hence, delta t is equal to 0. Next, we also know that there is nothing stopping a deformation in x or y direction. There's no support in this direction, so there will be no stresses either. Hence, we can remove sigma x and sigma y from this equation, since they're equal to 0. Hence we find that sigma z is equal to E times epsilon z or E times Y divided by R. And here you also see why it is important that the stiffness is the same in tension and compression, one of the assumptions we made at the start of this video. If this were not the case, we would have to multiply with a different value of the stiffness in tension and compression. So if we plot the stress graphically, it is also varying linearly as a function of y, with a compressive stress on top and a tensile stress at the bottom. This concludes the derivation of how the stress and strain distribution due to bending look like. In summary, we can say that due to bending, we get a compressive normal stress and strain on the concave side of the beam, shown in red in the figure below. We get a tensile normal stress and strain on the convex side of beam, shown in blue. There's also an axis of zero stress and strain, which we call the neutral axis. And once more, this does not have to be in the middle of the cross-section. And finally, we found that the stress and strain vary linearly with the distance from the neutral axis. So now we know the stress distribution is depending on the distance from the neutral axis, but we do not have a formula to calculate the stress yet. This formula is called the flexure formula, and we will derive this one in the next video. See you there.